everybody. Today we'll discuss about ideal and non-ideal gases. Okay. So we'll start with Boyle's law. Okay. And in Boyle's law, we know it very well, okay, that at constant temperature, pressure of a given mass of gas is inversely proportional to its volume. So if you equate this, then it will be P is equal to K 1 by V, where K is the proportionality constant. Okay, so I will get PV is equal to K is equal to constant. So whatever high the pressure is, if you multiply the corresponding volumes, that will give a constant value, which we can show taking a graph. Okay, how? So you have a graph like this. This is P. This is so PV versus P. Okay, and we have to show how PV is constant, how high the pressure is. Every point on this curve suggests you that the pressure into volume remains constant for whatever high the pressure is. Are you getting me now? So overall, now we are going to plot this graph PV versus P for only two different gas to have a have an interpretation of ideal and non-ideal gas, right? So you see what happens. Say when we plotted this graph for hydrogen, it took this trend, and the same when plotted for carbon dioxide, that took a trend like this. We have to discuss what happens for hydrogen and what happens for carbon dioxide so that they take this trend of the graph. We have another very important gas equation known as ideal gas equation. We all know that, okay? That is PV is equal to nRT, and we know the name is ideal gas equation. That means this equation is for ideal gas. So since this is ideal, this is for ideal gas, and since PV is equal to nRT, we will define a term called compressibility factor, that is called Z is equal to PV by nRT is equal to, and this should be 1 because PV is equal to nRT, and this is for ideal gas. And we know this curve is for ideal gas, since PV remains constant whatever high the pressure is. Okay, so you see, since this is Z, we are considering it compressibility factor. What this actually mean, right? Compressibility factor. Compressibility factor means how compressible a gas is. Okay, how compressible a gas is. That means, if you apply pressure, that means high pressure, then a gas can be compressed, and a gas can be compressed to liquid at very high pressure. Do you get me? So this is the compressibility factor. We can have this compressibility factor for both hydrogen and carbon dioxide, but now this Z is being defined for ideal gas, and since for ideal gas PV is equal to nRT, they are equal, so the compressibility factor for ideal gas Z should be equal to 1, and Z is equal to 1 for all ideal gases. Now the case is for hydrogen and carbon dioxide. What is the cases? And I have already mentioned the compressibility factor suggests you how compressible the gas is. Let us first discuss the case of hydrogen. You see, hydrogen is above this Z is equal to 1. This we consider the positive deviation. We say it? Yes, positive deviation. You see, in positive deviation, hydrogen is above the Z is equal to 1. Why this is like this? So it suggests us molecules of hydrogen have repulsive force. That means the repulsive force among hydrogen molecule is dominant as compared to the attractive force between them. Since they have repulsive force, and we know in ideal gas there is no attractive force nor any repulsive force. Okay, so since in case of ideal gas there is no attractive nor repulsive force, and this is the repulsive force which is dominant in case of hydrogen, what happens? You see, you consider a box here, right? Say these are the ideal gas. Okay, in ideal gases there is in ideal gases no interactive force, no interactive forces. Interactive force means attractive or repulsive force. Since there is no interactive forces, the molecules inside the box should strike the wall with a normal force, with a general force with which it should strike. But what happens in case of say hydrogen? Since we are saying in case of hydrogen there are repulsive force, so since one molecule of hydrogen, if we will consider this box contain now the hydrogen gas, one molecule when approaches the wall, the molecule behind it repel it, so that a molecule which is going to strike the wall will strike the wall with a greater force, because a molecule is coming behind it, and that molecule from behind will repel the molecule, so that will strike the wall with a greater force. Since it is striking the wall with a greater force, higher is the force, higher will be the pressure. So molecules of hydrogen have a repulsive force between them. What happens then? They strike the wall. They strike the wall with greater force than the molecules of ideal gas. Then the molecules of ideal gas. So what happens when the molecules of hydrogen strike the wall with a greater force as compared to the molecules of the ideal gas? What happens? It's now clear that higher is the force with which the molecules strike, higher will be the pressure they apply. Okay. So higher is the force with which molecules strike, higher will be the pressure applied. pressure applied. Okay, higher is the force, higher is the pressure applied. So what happens then? That means P, pressure of hydrogen is now considered as the real gas. What actually really exists in the atmosphere called real gases. So pressure of real gases means pressure of hydrogen is greater than pressure of ideal gas. Then P real V implies P real into V greater than P ideal into V, implies P real into V by nRT is greater than P ideal into V by nRT. Do you get me? Now this is clear. This is the Z for the real gas, means for hydrogen. This is the Z for the ideal gas. So implies Z for real gases greater than Z for ideal. So this is now the positive deviation. This is now the positive deviation. So that's why hydrogen is above this curve. Did you get me? But for carbon dioxide, what happens? What do you think? What type of force, interactive force, should be there in case of carbon dioxide initially? But you see, after some pressure, after this pressure, carbon dioxide also show positive deviation. We are not going to that. We are here to show the negative deviation, as because the curve goes down, the Z is equal to 1. So you see, what type of attractive force, what type of interactive force should be there? Yes, attractive force. Okay. So in case of carbon dioxide, there are attractive force between them. That attractive force, it's now clear what happens. As we just wrote for the hydrogen gas, due to repulsive force, the force with which hydrogen molecules should strike is greater than the force with which the ideal gas strike. Now due to attractive force, the same when this is hydrogen, this is carbon dioxide gas. When this is carbon dioxide gas, when one molecule of carbon dioxide is going to strike, what happens? When one molecule is going to strike the wall, another molecule from behind is attracting it, right? Since it is attracting it, the force with which a carbon dioxide molecule should attract the wall of the vessel is less now, because someone is dragging behind it, right? So since force is less, pressure will be less. P real, right? P real is now less than the P ideal. Okay. Since P real is less than P ideal, P real V is less than P ideal V. So now P real V by nRT is less than P ideal by nRT V. So Z real is less than Z ideal. So this is called the negative deviation. So see, this is the case what makes a gas showing positive or negative deviation. So in case of after this pressure, again when you are increasing the pressure, that means you are decreasing the volume. So molecules get closer. So there is distance limit within which there should be attractive force or there should be repulsive force. In case of carbon dioxide, the repulsive force becomes dominant when the molecules comes closer to a minimum distance. When the volume is that minimum, we get. You see here, this is also. You can compare this point also. Minimum and minimum. That means when we start moving in this direction, we are finding more and more attractive force. That's why the curve going away from the Z is equal to 1. That means this is the pressure when the repulsive force started. The repulsive force started. Okay, and this becomes very dominant when it reaches this and starts showing positive deviation. So positive deviation when started, that means repulsive forces become dominant, and in case of hydrogen, that repulsive force is always there